In this video, we will learn about negative chemical ionization and fragmentation patterns in mass spectrometry. It is the continuation of the previous video, in which we have dealt with the applications of mass spectrometry and positive chemical ionization. Now we will continue with the negative chemical ionization. In negative chemical ionization, the negative ions of the sample are formed and the oxygen and the hydrogens are used as reagent gases. In the previous case, in positive chemical ionization, there we have seen methane as a reagent gas. Here, hydrogen and oxygen are used as reagent gases. This method is used for ionization of highly electronegative samples. The negative ions are formed by the following reactions: resonance electron capture and dissociative electron capture. In a resonance electron capture, the neutral molecule accepts an electron and it is converted into anionic species. In dissociative electron capture, there is dissociation of bond as well as addition of electron happening in dissociative electron capture. The ion molecule reaction occurring between negative ion formed in the chamber source and the sample molecule include charge transfer, hydrate transfer, and anion molecule adduct formation. Advantages of this method is negative chemical ionization. Advantages of negative chemical ionization are: it is used for high molecular weight components, and it is used for samples which undergo rapid fragmentation in electron impact ionization. And it also has, the negative chemical ionization method also has some limitations. This method is not suitable for thermally unstable and non-volatile samples. It is relatively less sensitive than electron impact ionization, and the samples must be diluted with a large excess of reagent gas to prevent primary interaction between the electrons and the sample molecules. A schematic diagram of chemical ionization is shown here, in which the sample vapor goes, or it is injected, and inside the chamber it becomes a vapor. Inside the chamber, the vapor is present, to which the reagent gas is added, and there is a magnetic filament. The ionization happens, and the sample ions are passed into extraction and focusing lenses. That is, the focusing lenses pass the sample ions to the mass analyzer, where the mass analyzer analyzes the different types of ions according to their mass by charge ratio. Field ionization. It is used to produce ions from volatile compounds that do not give molecular ions by electron impact ionization. It produces molecular ions with little or no fragments. Application of very strong electric field induced emission of electron. Sample molecules in vapor phase is brought between two closely spaced electrodes in the presence of high electric field, 107 to 108 V per centimeter. If the metal surface has proper geometry and is under vacuum, this force is sufficient to remove electrons from the sample molecule without imparting excess energy. The electric field is produced by applying high voltage. In order to achieve a high potential gradient necessary to the effective ionization, the anode is activated by growing carbon microneedles or whiskers. As concentration of the sample molecule is high at the anode, ion molecule reaction often occurs, which result in formation of a protonated species. And that's the reason for observation of M plus and MH plus in field ionization method. The advantages of this method is, as fragmentation is less, abundance of molecular ion is enhanced. Hence, this method is used for relative molecular mass and empirical formula determination. And it also has some disadvantages, that it is not suitable for thermally unstable and non-volatile samples. It is sensitive. Its sensitivity is less than that of electron impact ionization source, and no structural information is produced as very little fragmentation occurs. Field ionization mechanism is shown schematically in the diagram. Let's move on to the mass analyzers. With the advent of ionization source that can vaporize and analyze molecules, it has become necessary to improve mass analyzer performance with respect to speed, accuracy, and resolution. More specifically, water pole ion traps, time of flight (TOF), time of flight reflection, and ion cyclotron resonance (ICR) mass analyzers have undergone numerous modifications, improvements over the past decades in order to be interfaced with MALDI and ESI. The first mass analyzer, made in early 90s, used magnetic field to separate ions according to their radius of curvature through the magnetic field. The design of modern analyzers has changed significantly in the last few years, and now offering much higher accuracy, increased sensitivity, broader mass range, and the ability to give structural information. Single focusing magnetic deflection, dense mass spectrometry. In this spectrometer, the positive ions travel in a circular path through 180 degrees under a magnetic field H. Suppose an ion having a charge E is accelerated through a voltage V. Then the kinetic energy of the ion is expressed as kinetic energy is equal to half mv square, that is equal to electron volt EV, where V represents velocity of ion after acceleration and capital V represents potential applied. It may be noted that a mass ion travels slowly in a circular path compared to the lighter fragment. In a magnetic field H, any ion will experience force HeV. It produces an acceleration of V square by R, in a circular path of radius r. Magnetic force equal to H EV. Single focusing magnetic field deflection, Dempster mass spectrometry. Next, Fourier transform ion cyclotron resonance mass analyzer, FTICR MS FTMS. Fourier transform ion cyclotron resonance mass spectrometry is a type of mass analyzer or mass spectrometer for determining the mass to charge ratio of ions based on the cyclotron frequency of the ions in a fixed magnetic field. FTICR is the highest performance MS technique available, offering unrivaled resolution and mass accuracy. A FTMS can be considered an ion trap system where the ions are trapped in a magnetic rather than in a quadrupole electric field. The ion cyclotron resonance mass spectrometer uses a superconducting magnet to trap ions in a small sample cell. This type of mass analyzer has extremely high mass resolution and is also useful for tandem mass spectrometry experiments. The FTMS consists of an ion source, some ion optics to transfer the ions into magnetic field, and the ion cyclotron resonance cells are pinning trap. Benefits of this: it is highest mass resolution of all mass spectrometers. It is well suited for ion chemistry and MS experiments. It is well suited to be used in pulsed ionization techniques like MALDI. It is non-destructive ion detection. Ion re-measurement. Mass calibration is stable in FTICR system with the superconducting magnet. The limitations are dynamic range is limited. Strict low pressure requirements demands a mandatory external source for a number of analytical applications. Artifacts like harmonics and sidebands are present in the mass spectra. Quality of mass spectrum is influenced by many parameters such as excitation, trapping, and reduction conditions. Generally, low energy collisions induce dissociation. Therefore, the spectrum depends on collision energy, collision gas, and other parameters. Applications are that it finds application in ion chemistry, high resolution MALDI, and electrospray experiments for high mass analytes, laser desorption for materials, and surface characterization. Types of ions produced in MS. First one is molecular ion or parent ion. Second is fragmentation ions. Third one is rearrangement ions, metastable ions, multiple charged ions, isotope ions, and negative ions. In this video, we have seen some application and of applications of mass spectrometry and types of ions. What are all the types of ions produced in the mass spectrometry? In the next video, we will elaborately see what is a molecular ion, fragment ion, a rearrangement ion, metastable ion, multiple charged ion, isotope ion, and negative ions. In the example shown below, that is in the spectra displays various peaks for ethyl benzene, in which we could see that there is a molecular ion with a maximum M/E value of 106, and we have a base peak at a M/E value of 91 with the maximum intensity, so it is a base peak, and there are fragment ion peaks also there. So these are the different peaks that we are going to see in the next video. Thank you.